So let us continue our session. And the next speaker is Jan Marquette from La Trobe University, who will talk about the commutant and construction of polynomial algebra. Please.
Okay, so I would like to thank the organizer for the opportunity to talk here. It's quite great. First time in BIMSA and in the area. So today I will try to talk about the construction of polynomial algebras. There is some connection in some way, maybe loosely speaking, with some talk this week, cluster algebras. But in our context, we will get set of polynomials that do not only commute or Poisson commute, but there is some additional polynomial that then allow to speak not only of integrability, but superintegrability. So when you have more conserved quantity. And I will also try to extend the discussion from superintegrability to another context that maybe we are not familiar with, missing label and dynamical symmetries. This is something that comes from the 60s when people were interested into describing various subalgebra chain and the corresponding shell model. So there is the Elliott chain, there is seniority, and they lead to a very interesting set of polynomial. But firstly, I would try to motivate from the angle of higher differential operators, where come, let's say, those polynomial algebras, and also maybe some, let's say, warning from us. There is many, let's say, ways to get integral of motion, often from classical approach, and we try to quantize. Classical and quantum integrability or superintegrability, they do not overlap when the integral of motion are third or higher degree. You get, in that context, Painlevé transcendent, higher order Painlevé, and in some way those rational functions for the potential are just in some way small set of the model that we can get. And something that I want also to advertise a little bit is if you use Poisson, let's say algebras, you can do things like relying on partial differential equation and tool from partial differential equations, and also the use of, I know that we like to have, let's say, very general formalism, but we can also deal with some package with polynomial with millions of terms. So in some way, if you want to get some concrete example, this is quite a good way to proceed with. Okay, so integrability and superintegrability. Here, this is just some definition. So a Hamiltonian system is integrable or Duville integrable because there is many formulation of integrability. For example, to nonlinear differential equation, you can speak about Darboux integrability. There is also non-holonomic integrability. In our context, this is Liouville, and we look for a set of n integrals of motion in involution, so the Poisson commute with the Hamiltonian and pairwise. They are functionally independent, and this is under the usual Poisson bracket. And so there is many examples, and to some extent, superintegrability is as old almost as Kepler's system. You can go back to some old paper by Hermann and Bernoulli from 1710, where they obtained the Runge-Lenz vector. It goes back to Pauli and early days of quantum mechanics. Here, this is just one review paper, still a bit outdated, but can give a lot of examples. Superintegrability, if you have more integrals of motion, and to some extent, superintegrability is a spectrum. As long as you have more integral of motion than degrees of freedom, it is superintegrable. It is minimally superintegrable, and you can go up to 2n minus 1. If you have a system of nonlinear equation, you don't necessarily need to speak about, because this in some way is the even case. So you can speak also of, let's say, the odd case where you don't make a distinction between coordinate and momentum. And there is some, and I think this is probably appropriate to speak about non-commutative integrable system or degenerate integrability, because when I will go to this construction with commutant, you don't necessarily make the count in the same way than when you have explicit realization in terms of coordinate and momentum. So just to give some, also an extra definition, you can define superintegrability without relying on the integrability. But of course, if you want to classify system, it is more appropriate to have already a set of commuting integral. And this has been started in the 60s, so on two-dimensional Euclidean space. So you look for a Hamiltonian that has two integral of motion. They are quadratic in the momentum. And then you look for compatibility equation, and you can solve the compatibility equation in classical and quantum mechanics. This has been pursued in two-dimensional conformally flat space. In some way, if you're in two dimension, it's not very exciting because there's not that much spaces to look at. But still, you get 59 model. They divide into 12 classes, something that has not been pointed out over the week. There's a lot of transformation that preserve integral of motion. Among them, there's the Stackel transformation. So if you want to speak about equivalence class, you need to understand what are the transformations that allow to map a system to another one. And this is, let's say, the backbone of the classification. Many properties have been obtained. Solvability. I can speak a little bit at the end about solvability. This is a funny word because depending on context, you may want to have different definition. In that context, you can have also some formal or algebraic way also to discuss solvability or quasi-exact solvability. Multi-separability. This is the property for a system to allow separation of variables in more than one coordinate system. They connect with the ASCII scheme of orthogonal polynomial. And what is the topic of this talk? They have nice algebraic structure. So this is something that, is one aspect of, let's see. Okay, good. So quadratic algebras. So I would spend a few slides before going to the commutant, and we enjoy working with set of polynomial. They appear in different papers. Probably they are appearing in even earlier references, I'm sure. But in the paper by Lévy-Leblanc on angular momentum, already there is some algebraic structure there. Paper by Higgs, Lemon. And in some way, what really started this proper study of quadratic algebras is some paper by Zhdanov, Granovsky, late 80s, also beginning of the 90s, where they have made various connections between quadratic algebra. So what they are, this is one example. This is a three-generator algebra. You could say that this is rank 1. This is something that is analogous to, let's say, the formation of SL2. But this has appeared also in disguise in various papers. For example, we can talk about Leonard pair and so on. So this is just one way to do it. But one thing that I want to emphasize is that you can actually obtain information on the quantum system using the algebraic structure, meaning that if you look at the Casimir, the representation, you can solve, without even solving a ODE, a PDE, what is the spectrum. Of course, every algebraic method, you need to be careful because they don't take into account boundary condition and some further aspect, because in some way that is part of the problem. This is just the anti-commutator. Yeah, in some way, this is something that is quite, not that much, but if you want to make this classical quantum correspondence, sometimes there is an advantage also to not only symmetrize the integral, but also symmetrize the algebraic structure. So you work with anti-commutator. Okay, good. Okay, so this is what I just briefly wanted to say. Because this will also affect this construction with commutant in the sense that I don't claim that you can obtain all superintegrable system, all polynomial algebras using just enveloping algebra of Lie algebras, because mainly of those developments. So I won't put any slide on this, but there is, let's say, work where you try to classify on two-dimensional Euclidean space and Riemannian space potential and integral of motion. And you get a large list of such potential, and the potential are written not in terms of rational function, trigonometric or elliptic, but they are written in terms of Painlevé transcendent. And in some way, this is probably the feature of superintegrable system. It means that when we see potential and they are rational, they are just the first layer of a large set of potential. Okay, and all those Painlevé transcendent appear, and this is quite interesting because it generalizes in some way the Lamé operator. Lamé operator is this second order ODE where as a function appear the elliptic Jacobi function here. This is Painlevé transcendent. And they lead to cubic, quartic, and polynomial algebra by trying to make commutation of their integral of motion. Okay, so here just one example. You can see that I didn't even give you the full operator. So this is something that looks like square of angular momentum. It's separated in polar coordinates, so it's straightforward. And then I don't give you this function and the other one. They would take one slide each. And this one is just one particular example of a potential written in terms of Painlevé 6. And we know that Painlevé 6 has 4 parameters, infinitely many rational solutions, many solutions in terms of hyper geometric. So in some way, this is one particular potential among a large cast. But if you now you need to believe me. You take this operator of second order, fourth order, you begin to commute. It closes in the following way. And this is something that is also a feature of this construction. The structure constants are no longer just, explicit constant. They depend on central element. If you're in 2 dimensions, the only central element is the Hamiltonian itself. So this is something that we will try to mimic when we will use the commutant construction. So this is something that we'll try to explain, let's say, this structure, also the form of the structure constant. And those structure constants, they will then be explained in terms of Casimir and in terms of other important, let's say, polynomial. Okay, so this is the backbone of this. You have this classification of superintegrable system. They lead you to interesting algebraic structure. But you want to understand what they are, because you cannot claim that you have understood the algebraic structure because you have some realization. So you want to, let's say, abstract a little bit things. So what we will try to do is to find, let's say, a commutant. So this is quite simple construction. You choose a Lie algebra, you choose a subalgebra, and you decide to look for polynomial in the enveloping algebra that Poisson commute or commute with that subalgebra. And by construction, it will be finitely generated if this is semi-simple or reductive. There is a lot of non-semi-simple algebra that in some way have nice property that you can also have closure there. I just want 2 more slides before I give the definition. Just to, as everything, there is people that have come up in some way with some related idea. I just want to say that because I will speak about the Cartan subalgebra, there is also wider work where they have looked at massas, so maximal subalgebras, and they almost obtain the commutant in the sense that they look from the point of view of differential operators. So you in some way, you have a small slice of the structure when you do that, but this is something that is quite interesting, that they have obtained those lists of Hamiltonian potential, very explicit from such construction. Another thing that I wanted to advertise, because I will use this in my construction, when you go to the Poisson setting, you don't want only to just use the fact that you manipulate commutative variable. You can recast the problem into PDEs, and you can then use a lot of criteria from PDEs to count the number of solutions, and then you can characterize that you got all the set of polynomial that you would expect. So this is something that has been done for Casimir invariant. Of course, commutant is a larger, let's say, problem than just Casimir invariant. Okay, so the main part of the talk will be about this work. So this is with various collaborators from Europe. So Danilo Latini from Milan, Rudwig Campoamont-Schussberg from Madrid, and collaborator from Australia in Queensland, Yao Zhang. And we have looked in this paper at the commutant of SLN and relative to the Cartan subalgebra. So it's something that is quite, let's say, more straightforward, but I will explain also some more general one. And you start with Lie algebra, you have the universal enveloping algebra, and very important for us, you have an ordered basis. So, and this is what you will work with, because when you work with the, let's say, the quantum or the Lie setting, every time you want to reorder your polynomial in your given ordering, which is quite computationally costing, But you can rely also on other idea. I won't explain on this, but we have in the paper more on that, root, grading, and certain decomposition. So you can understand in better way where the polynomial come from. This is just a definition of the commutant, but already explained. This is CUG, so I'm looking for polynomial in universal enveloping algebra of my Lie algebra G. And I look for subalgebra G prime, so I want those polynomials to commute with all the elements of that subalgebra. To some extent, if I choose G prime to be G, this is the Casimir invariant, and to some extent, if I choose a very large subalgebra, I might not get that much, more polynomial than the center of the enveloping algebra. Okay, and what I mentioned also earlier, if you look at certain of those problems, for example, SU2 cross SU2 in SU4, you will get a set of 20 polynomials of to degree 11. So, of course, if you want to close this as a Poisson algebra or as a commutator algebra, you will need to spend some amount of time with symbolic computation software. Okay, so this is just this, but it gives you directly a notion of superintegrable system because I can just pick up my preferred Casimir invariant, select some element from the subalgebra, and by construction, the element of the commutant will be integral of motion, and there will be a subset that will then commute or Poisson commute among each other. So I will have something that is like a cluster algebra, let's say, and those one will play the role as those n integral that commute or Poisson commute. Okay, so here you get a larger set than only those cluster. Okay, this construction, it appeared before. This is simply just, some canonical Poisson bracket. It comes directly from your Lie algebra. The structure constant appear there, but that offers you to build this one. So this is quite advantageous because you work with function of commutating variables. So then you can take derivative. You can take a lot of operation, but that is living in the symmetric algebra, and you can decide to go from one to the other using a symmetrization map. But again, symmetrization map is quite costly because if you want to reorder, a monomial of 6 or 10 variables, but you can do it again with that symbolic computation software that I mentioned. And this is just the commutant, but the definition in terms of the symmetric algebra. So this is just replacing with Poisson bracket. Okay, so what is the construction? Is to simply, you take your Lie algebra, your subalgebra, and then you will construct polynomial because you know that if your algebra is semi-simple or reductive, this is finitely generated, and it should be a finite list of polynomials, so you can just construct them every slice, so degree by degree, and you can filter the decomposable one. And to some extent, that's the key of this, is that at a certain degree, all the polynomial you will get, you will be able to write them explicitly in terms of the one that you know. So they will be decomposable, but you cannot get rid of certain relations because there will be implicit relation among your polynomial, and you cannot just take them out in some way because you want to work with polynomial, not rational function. And the idea is that if you deal not with a reductive or semi-simple algebra, you can then rely on this, set of PDEs, and then you can get rational function, transcendental function in that set, okay? And those can have other type of connection. For example, if you think about L'Octa-Volterra system, integral of motion, they are often rational function. They are often depending on logarithmic function. So you can get those using that sort of approach. Here, this is guaranteed that it will close in a Poisson algebra because I already told you that at a certain degree, they will all be decomposable. So if you take the Poisson bracket of two polynomials in your set, they can only decompose into those polynomials. So to some extent, it's something that is guaranteed to close if your algebra is semi-simple reductive. And you can quantize this straightforwardly. You just take the symmetrization of your polynomial, and you try also as much as you can to symmetrize as well. This will give you the leading term of the quantum structure. So you can symmetrize everything and you will get some correction out of it. Okay, so we were looking also for some example. Okay, so this is just a slide also to explain that your explicit Hamiltonian become a polynomial. It's a combination of Casimir and element of the subalgebra. The integral become your commutant either in the variable of the dual space or in terms of your Lie generator. And the polynomial algebra becomes something that is closed under the Lie or Poisson-Lie bracket. And I would just give some detail on the AN case. We did also the case BN, CN, DN, and you can play the same game with G2. G2 will lead you to 66 polynomial. It closes up to degree 6. But to some extent, we should not hope too many, let's say, nice formula. Because if I give you, for example, G2 and I ask for the Casimir invariant, we all know that the Casimir invariant of degree 6 is something that has a lot of terms. So to some extent, those things do not necessarily display always nice form. Okay, SLN, you can write, using GLN relation. And I will make a difference between those capital EIG. So I'm in the Lie algebra. When I'm in the dual space, this is the small letter, so E there. This is known because in some way this is like a parabolic, or partial trace in some sense. Those polynomials are known. And to some extent, what is this commutant? This is your Cartan generator because you are taking as subalgebra the Cartan generator, and also you will get those polynomial P I1 up to ID. But what you need to look for is decomposability. You need to look also for the algebraic relation. So you want to really obtain the set of, let's say, algebraically independent generators. So if I just look for n equal 3, I have two Cartan, H1, H2, and my polynomial are P12, P13, P23, P123, and there is also the P132, and they are related via that relation. It's not very nice, but this is everything that I need to know to construct superintegrable system out of SL3 with choosing the Cartan algebra as subalgebra. But this is not the best basis, so then you can play small games. Okay, this is the commutation relation, but it's already guaranteed that it closes. So in some way, that is not unexpected. So it is quadratic, but you can play different games. One of it consists to form other type of bases. Those one, they have some cyclic properties, so under the indices. And also you can play a game where you decide to not fix only 1, 2, 3, but you want to play with some index that are not defined. I will do that in some. But one game that you can play is to take the set of A with 1, 2. So this is just with some coefficient, and also with some, terms that depend on CI and CG, but those ones are central. And you can see that it closes in the following way, and it looks very much like what I told you in that slide with the 59 superintegrable system. This is the Racah algebra R3, so this is the rank 1. And you see that now there is some parameter, beta, alpha, gamma, but they take the form of polynomial in the Cartan plus the two Casimir. So in some way, this is very natural structure, and I could decide to then form my preferred superintegrable system using Casimir invariant and Cartan generator. And you can play, more games with geometry. You could look at Marsden-Weinstein realization where you would have 6 coordinates. Then you can decide to, which one is the momentum or which one is the coordinate. And then you could decide to be on the sphere. And then you will get the generic model on the sphere, from which you can get the 59 superintegrable system via contraction. So to some extent, that object there contains already all those 59 superintegrable systems, more or less, when you play with the explicit differential operator. But now you see that this is quadratic, and this is another, okay, this is just another form using, index, where I don't decide to play with the set of independent one, but I considered all the set of CIG, FIGK, and GIJK, and it goes in the following way. And you see that there is some constraint here. Those constraints have been observed also for those Racah algebra in context of superintegrable system. You need to have those closure relations. It's the same for some Cherednik algebra and also for Calogero model. There is extra set of relation that you need to take into account. So this is another way to write it, but something that I told you, but you see there is some ... This is just to say that you can obtain the quantization. I take those polynomials. I can then look for, writing in symmetric form, but then I need to reorder everything, and then I need to construct again the commutation relation, and you get some deformation term. I don't give all of those. And then you can also play other games. You can look at SL4, SL5, but already SL4 get complicated, but there is something that is a generic feature. The algebra you get is cubic. And the Racah algebra that has been observed in terms of superintegrable system is quadratic for every dimension. So it means that if you look from the side of a commutant, you get a larger algebraic structure. And the reason for that is the following, that if you use those Marsden-Weinstein type of approach and you use explicit differential operator, in the case of SL4, you get those second, third, and fourth order polynomial. All the fourth order polynomial will reduce to the second and the third order one. And the algebra will go from cubic to quadratic. And this is a generic feature. If you go to a commutant of SLN, the algebra will be of degree n-1. And only when you are in the realization, all those Casimir, but not just the Casimir, all those higher degree polynomial, they will go back to expression in terms of the second and third order operator. But that is a warning also for us in the sense that if we look for symmetries or integral of motion, should we look in terms of the Heisenberg algebra, so in terms of differential operator, in terms of coordinate, or should we do it in terms of commutant, so in terms of algebraization of those Hamiltonian? The count of the integral is not the same in that sense. Okay, and this is just some small reference that people were interested into the R4 and representation theory, but that point out that probably if you want to look at the representation theory, you should go back to the commutant construction. Okay, so okay, so this is just some, what I said, but I just want to say that this fit probably nicely into the following. People have been classifying Lie algebras, and they have been classifying also subalgebras. It's quite difficult because if you look at the Poincaré algebra, you have probably something like 169 non-isomorphic subalgebra, so this is quite large. But in some way, what I've been doing there with those commutant, you could do it for any subalgebra of a semi-simple or reductive algebra. So to some extent, that lead to many of those polynomial algebra. And just to convince you that they are interesting also from other point of view, there exists many type of embedding. We have seen some embedding, GLN-1 in GLN and so on. Those ones are regular embedding. There is embedding that break the structure of your Lie algebra. One of it is this O3 or SO3 in terms of SU3. And there is the notion of missing label. If you would like to characterize the representation using this subalgebra, your Casimir invariant are not enough. But then what do you need? You need operator or polynomial that commute with your subalgebra. So then this is still going back to the commutant. And in some way, what you will get from this approach is all the missing label operator, and you will get a polynomial algebra that describe in some way connection between those different set of missing label operator. So this is another work there, again, with collaboration from Europe and from also Australia. And just to give some explicit detail, but this is the Poisson algebra. Again, I won't give you the, let's say, the map. You can use the generator of, let's say, GL3, and you can write some linear combinations that are appropriate to get this embedding of O3 or SO3 inside SU3. I would just give you that the idea was to form this rank 2 tensor there for the T. So you have 3 generators, they form your, let's say, angular momentum, and you have 5 other generators that form a rank 2 tensor, and that has some application, let's say, to nuclear physics. Okay, so, but for us, it will be a mathematical game. And you can look for polynomial. And those polynomials, some of them, we already know them. We know there will be the Casimir invariant, so Casimir invariant of this SO3 algebra. There is other polynomial like P2. There is a linear combination between P1, 3 and P2, 3, which are third order. That is the cubic Casimir invariant. But there is other things. There is those fourth order polynomial, and they mix the L and the T. But you can see that they are homogeneous, and you can define also a grading. So this can facilitate to, let's say, get some further insight. But we know that the problem of the missing label for SO3 and SU3 has only one missing label. So in some way, here we have more operators. We have 2 operators of degree 3, 2 operators of degree 4. So we know that they cannot Poisson commute with each other. So this will lead to including another polynomial. But here, we made the proof in the paper that you don't have any other polynomial. This is the complete set of independent. Now there is some relation among them, but you don't have more than this. And here, because we like to write things in a nice way, there is some trace and there is also other formula. But this is slightly misleading because in some way, this is not because you can find a nice formula that when you look for the Poisson, let's say, bracket, that those relations will be very useful. You still need to use the explicit, let's say, relation. Okay, so there is some rescaling. There is some relation between D1 and D2. And this is a relation that means that this is decomposable. I can just remove one of those polynomial D. Here, just to explain the notation, if I'm using a capital letter, it means that this is not in the set of commuting, let's say, polynomial. So this is why I'm using B1, B2 in such way. They commute with everything. At this point, C1, C2, D1, D2. And again, the letter indicates the degree. So C, degree 3, D, degree 4, and F, degree 6. And then you track those relations. And you want also to form as many polynomial that is part of this, let's say, maximal set of commuting element. Okay? So then when you do this, you get just this very nice algebraic structure. This looks almost like the one that I gave earlier with that explicit Hamiltonian and those integral of motion. This is cubic. And now you observe that there is many structure constant. But now we have a sort of, let's say, further description of those structure constant. They depend on the subalgebra. And they depend also on the Casimir invariant. They might depend also on other type of polynomial because you might find also other polynomial that are part of the set. So C1, C2, C3. But in some way, if you want to look at the representation theory, this is still a 3-generator algebra. So this is something that we can study quite straightforwardly. And this corresponds to the algebra for all the missing labels of SO3 in SU3. And this is a common feature for those algebraic structure. Okay, I promise that we can quantize. Then you use, you could use end computation, but you could also rely on this, software and C algebra. Then what do you need? You need to reorder, to write symmetrization of polynomial of degree 2, 3, 4, 6. 6, that's a lot of term. So then you can do this. But then you need to be able not only to just symmetrize things, because you want to work with your basis. So you need to reorder those into your given basis. So then you obtain, but there is some ... I just give some of them. But you can play with very large polynomial. and you can get your deformation. So this is quite nice, again, algebraic structure. So this is something, again, this is cubic. And you see, because we mentioned earlier about this anti-commutator, you have, here this is a simple case, you have advantage to also symmetrize your algebraic structure. So you have some anti-commutator. And again, those alpha, beta, delta, epsilon, zeta, and so on, they depend on the set. So in some way, when this week many people talk about cluster algebra, the Poisson commute with each other, those C1, C2, C3, they are some cluster algebra. But here we have some larger set of polynomial, because the trick is that we don't ask a priori for a set of polynomial that all commute together. We want a set of polynomial that Poisson commute or commute with a subalgebra. And then it gives some more freedom. And then you can, we could also play games with this construction and look for superintegrable system in that context. Okay, I don't know what this SO3 and SU3 will lead, but I know that there is some connection with the Godin model in some way. So you could play some game there. Okay, just to give another example, because that one was, let's say, well-known, let's say SO3 and SU3. There is various subalgebra chain, and I want to make it very explicit because there is this, let's say, search for dynamical symmetries by Yakello. There was a group in Yale where they have applied, if you look at the, let's say, this, there is the periodic table, but there is this extended table where you have 3,000 elements. If you look for the nuclear reaction, you can explain with dynamical symmetries and subalgebra chain, but not very largely algebra. You can, with U6, SO6, and the different subalgebra chain, explain those, let's say, nuclear reactions. So in some way, looking at things like SO5 is not far off from actual application. And here what we will obtain, because in those models, people are typically using fermion and boson, those relations, they are valid for any realization you like of your Lie algebra. So you could then put back fermion, boson, or the type of operator. So in this setting, what I'm looking at, SU2 cross U1 in SO5, and then you can see that there is some of those U minus, U plus, U3, V3. This is the subalgebra, and then my algebra is defined by this. And this is probably the feature of many of those algebra, because you're looking at some embedding that is not regular. You might lose some time to have nice, commutation. But in that case, you can also write it quite nicely. But then you go to your Poisson setting, and you look for those set of polynomial. You can explicitly write them. So some of them, they will Poisson commute. They are a set of commuting polynomial. But again, not all of those, and they will correspond to all missing labels for that problem of SU2 cross U1 inside SO5, okay? And you can play this game, and then, okay, this is just taking into account some algebraic relation, decomposability. You want also to form as much element that commute with, let's say, those polynomials that as you can, and it closes again in a cubic algebra. Very nice structure. You could decide to quantize as you like, and this will describe also, let's say, if you would need for your problem a certain set of missing label, this will tell you everything that you need, provided that you quantize this one. Okay. Okay, and now this is something that I just want to mention. What I've shown you is just the tip of the iceberg. They are very nice. In general, those algebraic structure, they would be, let's say, quite involved. If you think about, this is the Surfond model, this is SO3 and SO5, or SU2 cross SU2 and SU4, you need to work quite hard. And there is some nice way to write sometimes the polynomial. There is some properties. For example, if I take the subalgebra and I look for Cartan generator, I can get some insight into the structure of those polynomials. So there is a way to work with, but that can lead you just so far, because if you go back to that problem of SLN and the Cartan subalgebra, all those polynomials were part of the weight zero space. So it means that after that, the root structure is not so useful to deduce the Poisson relation or the commutation relation. You need to work with other type of grading or other type of information on your polynomial. Okay, so here you see that there is, again, this notation, B, C, D. So some polynomial have a degree 2, degree 1, degree 4, no degree 1, degree 3, degree 4, up to degree 9, and that takes different number. This is the complete set that, characteristic the commutant. There will be some Poisson relation, and you can see that if you need to go up to degree 9 polynomial, when you take Poisson bracket, that lead you to very high degree. So how do you prove that everything is decomposable beyond that and that you get everything? So you need to do a lot of work for that. But at the moment, all those are, let's say, solved, and they appear in some various of those papers. So you can look at different, let's say, construction, but the one that we were finishing quite recently was this SU4 chain. And you can, as I mentioned, look at some grading. Again, this is not that straightforward, but you can get some explanation for the form. And also, we have postponed to use any reduction, any concrete realization, but you can then, at the end that you get this algebraic structure, your polynomial, put back some construction. Then you can decide to use Marsden-Weinstein, or you can decide to use other type of approach. But what I want to emphasize is that those algebraic structures, they are valid for any realization. So I could even play games. I could even take differential operator realization, but what about matrix differential operator or even other ones? So that can probably lead to constructing, let's say, other models. So we have started to look at some connection with geometry. And earlier in the week, there was Jungje Zhang that also explained how you can look at different construction from the geometric side. So this is something that we are trying to expand. So I finish, and I will be open for questions.
Thank you. Any questions or comments? Okay.
I think I have a comment rather than a question.
Oh.
So if you consider a pair of classical Lie algebras,
yes,
one is embedded into the other, and you consider the centralizer in the universal enveloping algebra, that centralizer is covered by Yang-Yang in type A or twisted Yang-Yang of Olshansky in other types. And if difference between ranks goes to infinity, so the structure of the centralizer is very complicated. That's very complicated algebra.
Yeah.
But when you go to infinity, keeping the distance of the rank fixed, this complexity goes away.
Yeah.
And so the centralizer is covered by those algebras, Yang-Yang or twisted Yang-Yang of Olshansky.
Yeah, exactly. So there is some connection with those Yang-Yang. What would be interesting is to see how this can facilitate to look at those problems. So, of course, there is ways even for this SU4 case to write things also in some, because they are homogeneous polynomials. So there is probably some of those constructions of the Yang-Yang that allow to write things in a nicer form, let's say. Yes.
Thank you. Yeah, my question is regarding that part. You have cubic Poisson bracket, right? Do you have any concrete integrable systems related? For example, from a quadratic or linear case, we have several concrete integrable systems related.
Yeah.
What is that?
But I mean that is among Euclidean space. Delta is just, I mean, the usual Laplacian on Euclidean space. This is just some harmonic deformation. And to some extent, here you see that in the 5 variables, so this is some potential that depend on the angle. I can even write that in terms of a function of Painlevé 6. And what I'm telling about the integral of motion, you will still have a second and a fourth order integral, and you will still have a cubic algebra. So you can see that there is, so this is one example of a cubic algebra. So you have infinitely many superintegrable systems, and that's the problem of the classification, because as you go to integral of motion higher than 2, you get Chazy equation, and those Chazy equation, to some extent, they have reduction to Painlevé, not necessarily all reduction to Painlevé, you get other things as well, but you get, and those Painlevé, they admit parameters, so for those parameters, you get infinitely many superintegrable systems. So in some way, the question is, you have in fact too many potential to look at, and they have nice properties. Like that one, I made just a small comment about exceptional.
So what is data? Data is a Laplace or something?
Yeah, Laplacian. And then the small fine print is that the wave function, if you look at this, is in terms of exceptional orthogonal polynomial. So this is something that maybe not all have heard, but when you look at orthogonal polynomial, you can start with the first degree, and you can then have and then all the degree. But exceptional orthogonal polynomial, you can have as many missing degree, and you can start with any codimension you like. Those superintegrable systems, there is infinitely many of those that connect with such wave function. So it means that when you think about the spectrum, when you think about most of the spectrum, your quantum number, they take, let's say, very regular pattern. When you go to those exceptional orthogonal polynomial, it means that you will have all in the spectrum, and the spectrum will have less regularity in some sense. So that's another thing.
Does it have a Lax pair?
That I don't know. No one have looked at that.
Okay.
Yes.
Thank you.
Any more questions? Comments? Then let us thank the speaker again.